Okay. Any questions before I get started? We're going to keep talking about topic 5 today. So topic 5 is all about inference on a mean vector. We started out with a multivariate generalization of a t-test, a one-sample t-test. Suppose you have multivariate data and you want to test with a hypothesis test, is the population mean equal to some particular value? Yes or no, give me a p-value for that assessment. Hotelling's t-squared. The vanilla flavor of it is the one-sample flavor. When we get to comparing two mean vectors, it'll be Hotelling's t-squared again, but it'll be a two-sample Hotelling's t-squared, just like there's a one-sample t-test and a two-sample t-test. We figured out what the test statistic is for the t-squared. It looks qualitatively like a squared univariate t-statistic, just replacing univariate calculations with matrix and vector calculations. It also looks an awful lot like a statistical distance. That's not by accident. So hopefully there's some intuition that makes this feel comfortable to you. The sampling distribution of the t-squared statistic. If the null hypothesis is true, then the reference distribution that we compare to is this one. It's an F after we scale it with a constant out front. So it's a scaled F. That means if you want to test, is mu equal to mu 0, you compute the value of t-squared for your data, and you ask, is that bigger than the critical value that comes from this distribution? So let me show you an example. Yes? The F distribution, what was the question? Standardized? It is there is such a thing called a non-central F, a non-central chi-square. That's when they have been shifted one direction or another. This is the standard F. Yeah. So let's go look at some data. I referenced this data set called container. It is contained in an R package. So you don't actually have a data set on eCampus called container, I don't think. We're going to just load in these data from the R package Hotelling. So just as some background, I told you before that R comes loaded with a bunch of goodies, but there are packages that contain custom goodies for specific tasks that users have put together, or researchers. And so those are packages, and you can download and then load them into R, and you have access to all of the custom stuff that's in that package. There is, for example, a package called Hotelling. It's not loaded by default when you open R. So in order to do stuff that is in Hotelling, I need to install that package, if it's not already installed, and then load it using the library command. What I'm going to do is go to eCampus and download not the data, but the script for container. If I can find it. There it is. So course content, data, no, sorry. Course content, scripts, data specific scripts. For some reason I have a folder called other. I should just pull all these out into the main folder, but this is where container.r lives. Container.r is just a text file that contains R code. So I'm going to save it on my hard drive. And if you double click it, depending on if you've ever opened a .r file before, and depending on what kind of computer you have, you may get a message along the lines of, I don't know what kind of file this is. Tell me what program to use. You can tell your computer to open the file with a text editor. On Windows, I like Notepad++. It's free, and it does highlighting and indenting and stuff intelligently. It recognizes code. On a Mac, I like Text Wrangler. I'm going to tell this computer, open container.r with Notepad++. And so here's commented R code relevant to this example data set. These data, let me just say something about them, are for containers. So think like large shipping containers, type that they put on barges and ship overseas. Each row of this data set is a container. And for each of the containers, we have concentration measurements of 9 elements. Titanium, aluminum, iron, manganese, magnesium, calcium, barium, strontium, and what's ZR? Anybody know? Zirconium? Okay. So we have numbers, quantitative numeric variables, 9 of them. And the first column here is GP. That's just short, in this case, for group, comparison group. There's 2 types of containers. So maybe these are containers from India, and these are containers from Australia or something. They're different types of containers. Eventually, we're going to use our 2-sample comparison inference tools to compare. Is there a difference in the profile of element concentrations between the 2 container types? But right now, we still are looking at just the simple case of a single mean vector. So we're going to ignore the second category. So I'm about to show you R code that looks at just container type 1 and does multivariate inference on the mean vector. I'm also going to ignore manganese. If you look at the data for manganese, it changes, it almost does not change at all. For group 2, it literally does not change at all. It's 0.002 for every single container. And for container type 1, it's either 0.004 or 0.005. Very nearly doesn't change at all. So that means there's virtually no info in it. 0 variation means 0 information. And if you were to, for example, ask for a 1-sample t-test using some data that take the same value 30 times, you'll get errors from R. You can't, for example, compute a variance estimate if the data don't vary. The variance is 0. I mean, you can compute a variance estimate, but it is 0. So I'm going to ignore manganese, and I'm going to ignore container type 2. We're going to look at 8 elements in container type 1. Here's my code. And at the very beginning, I have 3 packages that I want to load in or library in. Hotelling is the package that actually contains these data. I can't remember what I used DESC tools for. Plotrix is for drawing ellipses. So I'll probably have to install 1 or more of these. I'm going to copy and paste over to R. Anybody have exciting weekend plans? other than homework, of course. My in-laws are in town. Okay, so I need to install these packages. Let's find our download mirror. And let's get hoteling. Okay, now let's go get DESC tools. What that is. Let's try that. Sometimes this code right here is a year old. I used this last year. And you'll find sometimes that there are revisions to code, revisions to packages. And in this case, looks like maybe they changed the name of the package. Part of the fun of working with software. Okay, so this is going to give us problems, it looks like. I got an error message. Dependency is not available. So we've got an issue with this DESC tools. I'll see if I can get by without it. But I do need Plotrix. So let's get that. Once you have installed the packages, they are permanently installed on your computer. You still have to library them in, though. So we've just put the files on our computer. Whenever I open up R, every single time I open up R, I need to library in these packages if I want to use them. I'm going to comment out DESC tools since it appears to be a problem. But I should be able to library these other two. I got a warning message. Warnings are not as bad as errors. And it just says, warning, so let me just explain what this output is saying. I asked, please library the hoteling package. And it told me, loading required package corp core. What that means is that in order to use hoteling package, you also need this package called corp core. Hoteling depends on corp core. So it's giving me a message that I'm loading in corp core because you need it. And then when loading corp core, it noticed that that package is a little bit old. It was built under a previous version. That doesn't necessarily mean a problem. But we might, if we're worried, go look and see if there's an updated version of corp core to download. Most of the time, a warning message in R can essentially be ignored. It's not going to break your analysis. All right. So now we have loaded these packages into our R session. The main thing I wanted out of hoteling is the data set that we want to play with. Often, with an R package, it comes with some data sets, some example data sets. So I think I can say data package equal hoteling. and I get a summary of the data sets that came with hoteling. There's two data sets. There's bottle.df, there's container.df. Okay, so I want to play with container.df. In order to, if I just type container.df, it doesn't know what I'm talking about. But I know it's available to me in the hoteling package. The way that we get access to it is with a command like this. Data container.df. This will only work once we've libraried in hoteling, because these data come with hoteling. So you have to library that in, and then you have access to this example data set. So let's do data container.df. Nothing happens, but now if I type container.df, the data are available to me. FYI, suppose container.df contained 5 million rows. If I type container.df enter, it's going to print lots of stuff, more than I need. Things like head of container.df are handy for just show me the first so many rows. There's also a tail function, show me the last so many rows. And also remember that you can always customize what you see using square brackets for subsetting. Show me the third and fifth row and the fourth and sixth column. Once container.df is here, as you see, we can refer to it, access it, look at it, do calculations with it. Suppose we wanted to look at the numbers for aluminum in container type 1. First column tells me container type 1s followed by 2s. And aluminum is in the third column. So suppose I just wanted to look at the values of aluminum for container type 1. The first 10 rows are container type 1, and aluminum is in the third column. So I could say, for example, AL, call it whatever you want, is container.df 1 to 10, column 3. 0.929, 0.859, ... Another way to do the same thing is to say container.df $ column name. That .df indicates data frame. A data frame to R is like a fancy matrix. It's a matrix that has some bells and whistles attached to it. Think of it more like an Excel spreadsheet. A table, an array of information. With a data frame, one way to access individual variables, remember the variables are always in our columns, one way to access individual variables is to say data frame name, $ column name. So I could say container.df $ aluminum to only get that column, and then if I only wanted to look at the first 10 rows, I could say square brackets 1 through 10. Once I have limited my attention to the aluminum column, it's no longer a two-dimensional array. It's like a vector. It's just that one column. So in my square brackets, I don't have something, comma, something else. It's only a one-dimensional entity. So I just have 1 to 10. But that gives me the exact same result as the previous line. I could also say, so I'll stop doing that. There's multiple ways to do most things in R. Okay. If you want, let me just reiterate, if you want to access a specific column in a data frame, one way to do it is with the $ and specifically refer to the column you want. This is another way that you may or may not like. I use it sometimes. I'm not actually a huge fan of it, but it's called attach. And what happens when you say attach data frame name is each of the columns, each of the column names become as if they were an object themselves. So that after I attach, I should be able to just type AL and get that column. Right now I can't. When I say AL, it doesn't know what I'm talking about. Even though there's a column in that data frame called AL, as far as R's workspace is concerned, it doesn't know what it is. But if I say attach container.df, then it can be recognized kind of in shorthand. So if you're writing your R scripts and you've got data frames and long data file names, and maybe the column names are long, it can become a little bit tedious to do $signs all the time. So attaching is a handy way to do it. Yet another way to do it is the with command. So if I say with a data frame name, after saying with data frame name, I can refer to anything by their column names as well. I like this way probably the best out of all three of those. The thing I don't like about attach is there's not really an object named AL. You can act as if there is, but there isn't. And if you change this as if it's an object, if I were to say AL gets AL times 2, that does not change the data frame. It's more kind of like a mirror, it's like a copy. So I don't like attach because if you make any changes, you won't, there can be a disconnect. Okay. All right, so let's think about doing inference on the multivariate mean. We have, ignoring manganese, we have 8 elements. So I have an 8 vector. Mu is a vector with 8 components. And let's do a test. Does mu equal a particular value? And then next time we'll do a confidence region. So something that I need to kind of reiterate, this Hotelling's t-squared stuff has an assumption built into it that your data are multivariate normal. When you do a univariate t-test, there's an assumption that your data are univariate normal. That's why you check QQ plots and histograms and stuff when you do t-tests. Just like with a t-test in the Hotelling's t-squared test, our data need to be multivariate normal. If they're not multivariate normal, then who knows whether our results are right or wrong. P-values could be wrong, confidence regions could be off. So if your assumptions of a model don't hold, then you're kind of on shaky ground. You can't be confident in your results. So if I'm going to do this t-squared stuff, one early consideration is, do my data look plausibly multivariate normal? The last set of notes, topic 4, had some material on answering that question with a data set. And a couple of things were suggested. One, you could look at each variable individually and ask, is aluminum approximately normal? Is magnesium approximately normal? And if every single one of them is approximately normal, then that's not perfect evidence, but it's a good suggestion that multivariate normality may hold. Just FYI, it's possible to have every variable be normal univariately, but multivariately, they're not multivariate normal. possible to have that. So just looking one by one is not perfect. It's not ideal. But that's where most people start. If I want to do multivariate inference, much of the techniques require multivariate normality. And the easiest way to check that is one by one. So that's what this is doing. In the topic 4 notes, I showed you QQ plots. QQ plots are just plots of quantiles, and you're looking for straight lines. If you make a QQ plot, you're asking, do my data look like they came from a particular distribution? We can make QQ plots for normal distributions, chi-square, any distribution you want. We're mostly interested here in normality. So here, let me just make these pictures. You see QQ norm repeatedly. Each one of those QQ norms is saying, make a QQ plot to assess whether this variable is normal. So what I'm saying in the first line is make a QQ plot for the element titanium. I can refer to titanium directly by just calling titanium because we attached the data frame a moment ago. But show me titanium, and for now, let's only look at group 1. So I could say titanium square brackets 1 to 10. Yet another way to do that is to say titanium square brackets only return to me the values for which group equals 1. In R, if you want to ask yes or no, does this variable equal this value, you use a double equal sign. So that double equal sign is your way of asking R, true or false, are these things equal? Not a single equal sign. A single equal sign in R is used for assignment. Like if you want to create a variable named x that takes the value 2, you could say x equals 2. This is creating a scatter plot of quantiles. Over at the right is a second call called QQ line, and all that does is add the best fitting line to the QQ plot. So let me make all these and briefly comment. Making a multi-panel plot in R. This is a 3x3 plot. You can do that by manipulating the parameters, the graphical parameters. So there's a function in R called par, P-A-R. And if you look at the help file for par, you'll see there's lots of things that you can fiddle with regard to how things are displayed, how things are plotted. What I'm about to use is the argument mf row. And there's an entry for mf row and mf column. Mf row, if I say par mf row equals concatenate 3, 3, that means set up an empty plot with 3 rows and 3 columns. So I'm about to make a 9-picture plot, is what this is setting it up for. If you don't do this and then run all of these at once, it'll make the first one, and then it'll immediately override it with the second one, immediately override it with the third one, and so on. So it's handy to write, or it's handy to at times make multi-panel pictures like this one. Again, QQ plots, you're looking for straight lines. The titanium picture with just 10 observations, QQ plots are difficult to really interpret very much, but that looks reasonably straight to me. Obviously, it deviates a little bit here and there, but it looks reasonably like it's following a straight line. So titanium, I'm comfy saying that's approximately normal. Aluminum, kind of, so, you know, a little bit. There's a little bit of a deviation up on the top right. That's concerning. Iron looks really bad. There's one point that is way off from where we expect it to be if the data were normal. Manganese, we might as well just ignore it anyway because it doesn't change almost any. Magnesium, a little bit of deviation up here. Calcium, same thing. Strontium, pretty strong deviation. And zirconium, pretty strong deviation. So overall, looking at these pictures, I would say the assumption of normality for all of them seems pretty suspect. If these individual variables don't look normal, then I'm confident they're not multivariate normal. I said earlier it's possible to have each of them be individually normal, but still not have multivariate normal. But if any of these are not normal, then you know it won't be multivariate normal. So if multivariate normal, then individual normality for all the variables, but not the other way around. All right, so again, based on that picture, not real comfortable with the multivariate normality. That's not going to stop us for the purposes of illustration, though, in this example, from using our techniques. The next chunk of code is something that we'll use further down. What I'm doing is consistent with the kind of notation I'll use throughout the class. We're going to say n, little n, is for the sample size. That's the number of individuals, the number of rows in the spreadsheet. And we're going to use p to be the number of variables. In this case, once we throw out manganese, we're going to have 8 variables. P is 8. And then these commands, x bar 1, x bar 2, s1, s2, these are computing the sample mean vectors, one for each container type. X bar 1 is the 8 vector containing the sample means for container type 1. And x bar 2 is the same thing except container type 2. S1 is a sample covariance matrix for container type 1, and then S2 for container type 2. For example, this command, x bar 1, it's looking at my container.df data frame, and it's subsetting to only look at the first 10 rows, because that's container type 1. And for the columns, it's pulling out the first and fifth columns. It's considering all the columns except the first and fifth columns. So the first and fifth columns are the group and 2, 3, 4, 5 manganese. I don't need the group for a t-test. That's just like an indicator or a factor. I want the numeric variables. So I'm going to get rid of the first column, and we decided to get rid of manganese as well. So this is saying, go give me the subset of the data frame that excludes the first column and excludes the fifth column and only includes the first 10 rows. Then to get x bar, the vector x bar, there's multiple ways to do it. One easy way to do it is with the call means function. That's like column means. Go column by column and compute the sample average. Once I subset the container data frame like this, I have a 10 by 8 array. So when I say call means, it's going to go through each of the 8 columns and give me back a sample mean. X bar 2 does the same thing, except it shifts down to be the last 10 rows for container type 2. And then down here, it's the same data frame subsetting. Give me the first 10 rows and exclude the first and fifth columns. But then I'm asking, I'm calling the var function, var. Var does multiple things depending on what you give it as an argument. If you just give the var function some numbers, like 1 to 5, it gives you back a scalar. That's the sample variance of the numbers 1, 2, 3, 4, 5. But if you give it a matrix, a two-dimensional array, then it's going to give you a matrix back of covariances and variances. So var either gives you a scalar or a variance-covariance matrix. In our case, we have a 10 by 8 matrix of numbers. So I'm going to get back a matrix of what dimension? How many rows and columns is S1 going to have, do you think? 8 by 8. Because I have 8 variables that I'm considering, and the variance-covariance matrix is that number by that number. The diagonal contains the variances, and the off-diagonals contain the covariances. So let's run all of this. Now P is 8. X bar 1 is the 8 vector, the sample means for container type 1. And S1 is the 8 by 8 matrix of covariances and correlation, variances and covariances. That's really ugly to look at. You could make it a little bit easier to see by rounding to a smaller number of significant digits. So let's round it to 4 significant digits. Easier to look at. I'll skip this part. This is also from topic 4, and it's a slightly more sophisticated way of asking, do my data look multivariate normal? What we did above was, let's just look at each variable individually and use QQ plots. Topic 4 showed a, again, slightly more sophisticated way for checking normality, and it's specific to checking multivariate normality. So it is better than those QQ plots. See topic 4 if you're interested. But I definitely want to illustrate this Hotelling's t-squared stuff. So let's come down here, and let's do a multivariate one-sample t-test. Hotelling's t-squared test for one mean vector. We're going to focus attention on the first container type. And just for simplicity, I'm going to limit our attention even further to only 3 elements: titanium, aluminum, and iron. We could use all 8, but it's easier to see things with a smaller number of variables. So just to illustrate things, let's look at just titanium, aluminum, and iron. Our null hypothesis, I made this up. You could pick whatever you want as a null hypothesis. But with a multivariate mean, the null hypothesis is that the mean vector takes a particular value. We could, for example, say that the mean of these 3 numbers is 0, 0, 0. I picked a different set of numbers just because these are a little more in line with the observed data. Suppose we had, contextual reason to think that these are default concentrations. 0.035 is the mean for titanium, 0.9 for aluminum, 0.15 for iron. I want to test, do my data look like they came from a multivariate normal distribution with that mean vector? When we do inference, we have to specify our confidence level. We're going to use a confidence or significance level of 0.05. Okay, so my null mean, I'm going to call it mu underscore 0. Underscore 0, just like h underscore 0, is our null hypothesis. I'm redefining p to be just 3 because we're only looking at the 3 variables. Then I'm going to compute my observed x bar vector. Now it's only 3 components, and my 3 by 3 observed sample covariance matrix. So let's just run all of those. And now we're ready to actually do the Hotelling's t-squared test. So step one is to compute the test statistic. If you wanted to do a univariate t-test, for example, you'd have your observations, you'd compute x bar, you'd compute s, and then the t-statistic is x bar minus what you think the mean is under the null, divided by s over the square root of n. That's your test statistic. We need to compute our test statistic. And the t-squared test statistic is of this form. So with multivariate data, I need to compute the mean vector. I need to compute the sample covariance matrix. And then once I write down what I think the null mean is, I can just compute this. That's what I have highlighted here. T-squared is n times the difference between x bar and mu 0, matrix multiplied by S inverse, matrix multiplied by x bar minus mu 0 again. It's not absolutely necessary, but just to be consistent, I'll go ahead and include the transpose. So the definition over here is x bar minus mu 0 transpose. Let's look at this one. X bar minus mu 0 transpose, S inverse, x bar minus mu 0. And there's an n out front. The t-squared statistic is 93.02777. In terms of making a decision, we need to then ask, is that extreme relative to the null hypothesis? Is that consistent with the null hypothesis, as in that's a realization that would be normal, probable, if the null were true? Or is this way out in the tails of the null sampling distribution of our statistic? To answer that, we need this result here. If the null is true, then the distribution of t-squared is this mess. So what I can do is take my t-squared value, the 93, and put it up against this distribution. If my 93 is way out in the tails of that distribution, the p-value will be really small, and that gives me evidence to reject the null hypothesis. So we can, for example, compute a p-value. The p-value is the probability of observing a test statistic as or more extreme as ours when the null hypothesis is true. When the null hypothesis is true, my test statistic is a scaled f random variable. So the p-value is going to be a right tail probability for this f distribution evaluated at my test statistic. Let me draw a note on our whiteboard here. We have, for the container data, we have a t-squared value of 90-something, 93.03. And we know that under the null hypothesis, so our null hypothesis is that mu equals 0.035, 0.9, and 0.15. Under the null hypothesis, t-squared is distributed as n minus 1 p over n minus p f p n minus p. Another way of saying that, that's equivalent to n minus p times t squared divided by n minus 1 times p is distributed f, p, n minus p. Just by multiplying both sides by the inverse of what the constant is on the right. The reason that's handy to do is because in R, we have built-in functions for computing arbitrary probabilities from named distributions, like the normal, chi-square, f. What I need to do for a p-value is then go to the f distribution. Here's the f with p and n minus p degrees of freedom. And let's say here's our observed value of n minus p t squared over n minus 1 p. That's the observed statistic value. P-value is the tail probability. What's the probability of seeing a statistic like ours, or even more extreme, when the null hypothesis is true? And if that tail probability, that p-value is small, then that's indirect evidence that the null is probably not true, because it'd be very unlikely to see what we saw if the null was true. So in the code, I'll leave you with this. This is a mess, but it's just doing what I wrote down on the whiteboard. P-value is 1 minus PF of stuff. PF, just like we have R norm, D norm, and so on, P norm is a cumulative probability function, a CDF, which is a left tail probability. So if you do 1 minus PF, then you get a right tail probability. I'm saying give me 1 minus the CDF, so the right tail probability, in the F distribution, evaluated at that mess, and this F distribution has P0 and n minus P0 degrees of freedom. So let me just run this. The p-value is 0.000458. That's a really small p-value. So we have evidence to confidently reject the null hypothesis. I am not comfy with the claim that that's the mean vector. It could mean that the first two are right, but the third one's wrong. Or it could mean that the first one's wrong, but the other two are right. Or it could mean that you're wrong at all three positions. All we're saying is that's not the mean. We're not comfortable saying that's the mean. In R, as with many things, you can do this multiple ways. And there is a Hotelling's t-squared test function. Comes with the Hotelling package. So just to make you feel comfy, damn, where is that? Oh, I bet that's what's in the DESC tools function. So take my word for it. If you use the built-in function, you get the same result. And we will do that with some other functions. Just the one sample Hotelling t-squared test, I don't think it comes in the Hotelling package. That's why I had the DESC tools function. All right, so that was a lot of info, but now you have hopefully a reasonable comfort level with t-squared tests. We're going to see t-squared tests for the next several lectures. And you have an example of how to actually compute it and a p-value. So it looks confusing, lots of constants and stuff floating around. We'll do the same kind of thing multiple times, so you'll get practice with this type of thing. Okay?